Okay, I guess I'll
Okay.
go ahead and get
Yeah.
started. Hello, everyone. My name is Addie. I'm a senior here at Tulane, and I'm going to be talking about the primitive prime divisors of the Catalan sequence today, which is a subset of my work that I'm doing for my honors thesis right now with my advisor, Dr. Mole, who I believe is in the audience. So thank you for being here. Yeah, so I'll just get into it. Okay, so first I'm going to start by defining what a primitive prime divisor is, since that's in the title of the talk. And the context that we're working in here is we're looking at integer sequences, and as usual, P is going to be a prime. And for a term AM in a sequence, we say that a prime P is a primitive prime divisor of that term if it divides that term, but does not divide any of the previous terms in the sequence. So in other words, a prime is a primitive prime divisor when it first appears as a factor of a term in a sequence. So as you can imagine, the kind of ideas that we're thinking about here is we're thinking about prime divisibility of terms and sequences, but we're also looking at when these primes occur. And really what we're interested in is when is the first time do you find a prime in a particular sequence. What do we want to know about primitive prime divisors? Well, there are lots of different questions that you can ask. There's lots of different questions that I've asked, but today I wanted to focus on one that I thought was particularly interesting. And so that is, given a particular term in a sequence, how many primitive prime divisors does the term have? And it turns out that you can find sequences where you have terms that have a varying level of primitive prime divisors. Sometimes you can find several primitive prime divisors for a term. Sometimes you can find terms or sequences where all the terms only have one primitive prime divisor. And this also means you can ask the question, what terms of the sequence have no primitive prime divisors? And this is really what I'm going to be focusing on in this talk, because this turns out to be a really interesting question to ask. So the terms that have no primitive prime divisor, these are terms where all of their prime factors have already appeared somewhere previously in the sequence. So they're kind of composite with respect to the previous terms in the sequence. And I'm going to introduce a definition that's going to help us kind of have a framework for asking this question, and that is the Zygmundi set for a sequence. And the Zygmundi set for the sequence is the set of all the indices for the terms which do not have any primitive prime divisors. So you take all the terms in the sequence that have no primitive prime divisors, you collect their indices, you put them in a set, we call it the Zygmundi set. And this is really useful for us because when we ask the question, which terms of the sequence have no primitive prime divisors, it's the same thing as asking the question, what is the Zygmundi set of the sequence? So this is just some terminology that's going to help streamline our question. And Zygmundi set comes from a mathematician, Zygmundi, who worked on these kinds of ideas way back in the 1800s. And Zygmundi's famous result is for the types of sequences a to the n minus b to the n, where a and b are coprime positive integers. And he said that the indices which have no primitive prime divisors are the indices n equals 1, 2, or 6. So in other words, the Zygmundi set of this type of sequence is a subset of the numbers 1, 2, and 6. Now, I thought this was really surprising because this means that the Zygmundi set is finite. So there are only a finite number of terms which have no primitive prime divisors, or most of the terms, in fact, all the terms where the index is at least greater than 6 have all have at least one primitive prime divisor, which means the sequence is kind of generating new primes at a pretty high frequency. And moreover, Zygmundi goes to state explicitly for which A and B does what's the Zygmundi set for those for that sequence. And this is actually a pretty good way to kind of illustrate what we're thinking about here. So Zygmundi's theorem says that 1 is in the Zygmundi set if and only if A minus B is 1. And this is really easy to see because if you look at the first term, we look at a to the 1 minus b to the 1, and that's a minus b, and that's 1. And since 1 has no prime divisors, it certainly can't have any primitive prime divisors. So 1 is in the Zygmundi set in this case. 2 is in the Zygmundi set if and only if a plus b is a power of 2. So again, if we want to see this, we can look at the second term in the sequence. This is a term indexed by 2, and that's a squared minus b squared. And we can factor it as a plus 1 or a plus b times a to the 1 minus b to the 1, Well, a to the 1 minus b to the 1 is the first term in the sequence. So we know that any primes that divide this first term can't be primitive for the second term because they've already appeared in the sequence. So if we want any primitive divisors, they have to come from this term a plus b. But remember, we said that a plus b is a power of 2. So its only prime factor is 2. And so if 2 is primitive, it means that 2 can't appear in the first term. But it turns out that if a plus b is a power of 2, then a minus b is even. And a little algebra, you can see that. And that means that 2 is not a primitive prime factor of the second term. It's actually a primitive prime factor of the first term. So this is when 2 is in the Zsigmondy set. And then finally, we see that 6 is in the Zsigmondy set if and only if a equals 2 and b equals 1. So this is a much more specific circumstance. But again, we can see this by looking at the sixth term in the sequence. And that's 2 to the 6 minus 1 to the 6, which is 63. And that factors is 3 squared times 7. So if we want to show that this has no primitive prime factors, we need to show that 3 and 7 appear somewhere in the sequence before the sixth term. And in fact, 3 is the second term of the sequence, and 7 is the third term of the sequence. So they're not primitive with respect to the sixth term. And I should also note that this sequence right here, 2 to the n minus 1 to the n, or just 2 to the n minus 1, is known as the Mersenne sequence. And this is a really cool sequence, and I'm going to talk about it a few more times in this talk, so keep an eye out for that. The next thing I want to talk about is generalizing this Zsigmondy result to more general classes of sequences. So in particular, we're going to talk about Lucas sequences. And Lucas sequences are actually pretty familiar to a lot of you. I'm sure you've heard of some types of Lucas sequences, which I'll talk about in a second. But don't get too tripped up about this definition if you've never seen this before. What you should really take away from this is that Lucas sequences satisfy this type of second order recurrence where you have integer coefficients p and q. And there are two kinds of Lucas sequences. The first kind have the initial conditions 0 and 1, and the second kind have the initial conditions 2 and p. So even with the same coefficients p and q, you can get different sequences based on the initial conditions. So we have two kinds of Lucas sequences. And just as an example, that sequence we were looking at before, the Mersenne sequence, it can be written as a Lucas sequence using this terminology, and it's a Lucas sequence of the first kind with coefficients 3 and 2. And you'll have to believe me for now, but the Mersenne sequence satisfies this recurrence right here, which is exactly what this notation tells us. There are also lots of other well-known Lucas sequences. So like I said, you've probably heard of the Fibonacci numbers. Maybe you've heard of the Lucas numbers, the Pell numbers, the Jacob-Stahl numbers, the Fermat numbers. These are all different types of Lucas sequences. And in 1913, a mathematician named Carmichael showed that for a particular type of nice Lucas sequences of the first kind, the Zsigmondy set of these sequences is again a subset of the indices 1, 2, and 6. Except for the Fibonacci numbers, which have a special Zsigmondy set that is 1, 2, 6, and 12, but they're the only exception to this rule. And so again, we see here that the Zsigmondy set for these sequences is finite, which I think is really interesting. And now you might be wondering, hey, Addie, what does nice mean? You're not giving us a lot of information there. There's a few different things that go into the word nice here, but they're not really important to us anymore because in 2001, it was shown that you can actually have any Lucas sequence of the first or second kind, or any Lemma sequence, which is a generalization of the Lucas sequence. And we can find that the Zsigmondy set is finite, and it consists of the numbers from a subset of the numbers from 1 to 30. And moreover, their paper determines explicitly where you can find the elements of the Zsigmondy set given a particular sequence. So very similar to Zsigmondy's result, but now expanded to a really large class of integer sequences. And you also might be wondering, why do we care about primitive prime divisors? Well, there are some ways that we can think about primitive prime divisors that help us understand things about sequences. So remember that Mersenne number sequence that we talked about before. It's an open conjecture that there are infinitely many terms of this sequence, which are prime. And the most current formulation of this conjecture is known as the Lenstra, Pomerantz, and Wagstaff conjecture. So to kind of illustrate this, the second term of this sequence is 3, which is prime. The third term is 7, which is prime. The fourth term is not prime, but the fifth term is 31, which is prime. So some of the terms of this sequence end up being prime. And there's this project called the Great Internet Mirroring Prime Search, which is a collaborative internet project. And their goal is to search for the next largest Mersenne prime in the sequence, because it turns out that this is one of the best ways we have of generating really large primes that we can use in cryptography, for example. And in fact, the largest known prime is a Mersenne prime, and it's this number right here. And I believe it was found in 2018 by the GINS project. So relating this back to Zygmondi's theorem, remember that Zygmondi's theorem tells us the Zygmondi set for the Mersenne numbers is finite. So we know that for any term of this sequence with index greater than 6, we're going to get a new prime factor that hasn't appeared in the sequence before. So like I said, this sequence is continuing to generate new primes at a really high frequency. In fact, at least one new prime per new term. And this is definitely not the same thing as the infinitely many Mersenne prime conjecture. It's definitely a weaker statement, but this is sometimes cited as heuristic evidence to support that this is in fact the formulation of the conjecture that we should be trying to prove, which is good for us, because if this conjecture turned out to be false, it would have some pretty unfortunate consequences. So that's just one way that we can use the idea of primitive prime divisors to help us kind of understand other problems in mathematics. So now we're going to move on to some of my research that I've been working on. And so I saw the idea of primitive prime divisors, and I thought that was interesting because I was working on some other work looking at prime divisibility of sequences related to the Catalan sequence. And so I thought it would be interesting to look at what the primitive prime divisors of the Catalan sequence were, since the Catalan sequence is not a Lucas or Lemmer sequence. Now, the Catalan sequence is, if you've never seen it before, it's given by this formula right here. There's lots of different formulas for it, in fact, but it uses binomial coefficients. Can also be written in terms of factorials. And the cool thing about this sequence is that it has hundreds of combinatorial interpretations. So a large number of problems in combinatorics tend to involve the Catalan numbers in their answers, which makes it a really interesting counting problem, as well as just an interesting sequence. So my question was, again, what is the Zygmondi set of the Catalan numbers? So in order to kind of try to reason what the Zygmondi set for this sequence might be, I was interested in looking at this particular recurrence of the Catalan numbers. Now, there are several different recurrences, but this one is a really nice recurrence because it's a first order homogeneous recurrence. So the nth term is related only to the nth minus 1 term. And also there's no kind of extra term out here that's being added or subtracted to the sequence. And this gives us a really nice framework for thinking about primitive prime divisors, because our sequence has kind of a multiplicative construction. Now, we don't have to worry about how addition or subtraction is going to change our sequence as we increase our terms, which is going to make it easier for us to deal with prime factors, since we don't really know a lot about how addition changes prime factorizations. And in fact, if we want to think about how we would get a new prime factor for this sequence, given we've already seen a bunch of terms, a bunch of prime factors in the previous terms, where would we find this new prime factor coming from? Well, we certainly wouldn't find it coming from the nth minus 1 term, because then it wouldn't be primitive since it would have already appeared in that term. So we know that it has to come from this coefficient out here. And in particular, it has to come from the numerator here, because we know that the Catalan numbers are integers. So this n plus 1 is going to somehow cancel out somewhere. And again, the kind of 2 appears here, but we're really interested in mostly the odd prime, since we know that 2 is already going to appear somewhere in the sequence pretty early on. So it turns out that this is actually exactly what it is, that this term 2 to the n minus 1 is what determines the Zygmondi set. So in this case, n is in the Zygmondi set when 2 to the n minus 1 is not prime, except for 5, which is an exception. And I'll get to that in a second. But the idea here is that if 2 to the n minus 1 is prime, then it's going to generate a new prime factor that we've never seen before, and that term's going to have a primitive prime factor. But if 2 to the n minus 1 is not prime, then it's not going to generate any prime factors that we haven't already seen before for that term. So therefore, that term's index is going to end up being in the Zygmundi set. Now, one thing to note here that there's a lot more that goes into this argument to kind of prove this theorem. And one of the interesting patterns that you can show is that one of the questions I was interested in is what order do the primes appear as primitive prime factors in this sequence? And it turns out that for the Catalan sequence, with a finite number of exceptions, the primes appear in their natural order as primitive prime divisors. So if you've seen the primes up to 7, you know that the next time you're going to find a primitive prime factor, you know that's going to be the prime 11, which is kind of helps this argument play out. And now this kind of 5 exception comes from something some of you might have noticed, which is that if what happens when 2 to the n minus 1 is equal to n plus 1, and this gets canceled out. And that's kind of the situation that ends up having this exception right here that you have to deal with. But that's the only exception, and it happens really early on, so it's pretty easy to deal with. And then to move on to kind of the future work, or I guess the work that I'm doing currently right now, is I was interested in taking that result for the Catalan sequence and showing it for other types of related sequences. And in particular, I was interested in the sequence that's called the kth convolution of the Catalan numbers. And so it's given by these formulas right here. There's a couple of different ways you can write it that are equivalent. And the idea is you fix a k and you index on n, and it gives you an integer sequence, which is really cool. And you'll notice that this is similar to the formula of the Catalan numbers, but now we have this extra variable k, and it turns out that actually when k equals 1, we get exactly the Catalan sequence. And they're called the convolutions because they come from convoluting the generating function of the Catalan numbers k times. So I was interested in looking at the primitive prime divisors of this sequence, particularly because this sequence preserves the really nice property of the Catalan numbers of this first order homogeneous recurrence. So this is the recurrence for the kth convolution sequence. And I wanted to know if it was also going to be true in this case that the numerator of this coefficient out here was what's determining the primitive prime factors of this sequence. And that's my conjecture right now, that those numerator terms are exactly what's determining the elements of the Zygmundi set. But now we have to deal with the parity of k, because we know that, for example, in this case, if k is odd, then this number is going to end up being an even number. So we know that it can't generate any primes if it's only generating even numbers. And you'll notice here in my conjecture that I'm saying this is only for kind of large enough n. And that's because when n is small, we run into similar problems that we did at the Catalan sequence with 5, where n and n plus k end up canceling terms in the numerator, and that gives us some problems. And that's what I haven't quite figured out yet, and what I'm still working on, but I'm hoping to generalize. So, and just one more note that I think is kind of interesting that I saw here was in the case of the Lucas and Lemmer sequences, we saw that the Zygmundi set was finite, and that the frequency at which those sequences generated new primes was quite high. In this case, we find that the Zygmundi sets are not finite, they're infinite sets, and they're generating primes at the frequency at which I guess odd numbers generate primes, or where primes appear in the odd numbers. So a much lower frequency of prime generation for these types of sequences. So that concludes my talk. Like I said, this is very much ongoing work for me. So if you have any feedback, comments, or questions, I'd be really appreciative to hear them. And I also like to give a shout out to Dr. Mole, my advisor, and also Dr. Joyce, who's the second reader for my thesis. And I believe he's in the audience somewhere too. So thank you both for coming to support me. Yeah, that's it.